Hello everybody and welcome to chapter 1.2 of Calculus and Vectors. Today we're going to start a brand new topic, so I hope you enjoy that. Today we're actually going to talk about rates of change using equations, because if you remember before we were talking about delta y over delta x, which is not really an equation in itself because you are not solving for anything. So today, we're going to talk about two different things. We're going to talk about how to derive the equation and also how to apply it. So let's get started on that. Deriving the equation is pretty simple. So for example, you have a function y is equals to f of x. We know that the rate of change over some interval, let's say from point A to point B, can be determined by calculating the slope of the secant, which is of course delta y over delta x. So what is y here? Well, the first y would be f at a, right? And the second y would be f of b. So putting those values into delta y over delta x, we should actually get this equation here, which is f of b minus f of a divided by b over a. This right now doesn't allow us to do anything too useful because we still have two unknowns with two different points. However, we can express b as the sum of a and the distance separating point A and point B. So in this case, let's call that distance h. So now, substituting a plus h for b, we actually get f of a plus h minus f of a divided by a plus h minus a. Of course, a minus a is nothing, and so we actually get f of a plus h minus f of a, all divided by h, which is again the distance between points A and B. So this expression here is actually called the difference quotient. This quotient is super important to remember because that is kind of the foundation of the rest of the book. Understanding how to use this is super important, and it's also really necessary for you to understand what it means. Again, h is the distance and a is some point that we want to evaluate. So if we were trying to evaluate a function like its rate of change at 3, a would be 3, and then h would be the distance we need. So if we were talking about the average rate of change between 3 and 5, h in that case would be 2, because the distance between 3 and 5 is 2. This equation is also super useful for determining instantaneous rate of change. However, there's a little bit of a trick to it. So again, for instantaneous rate of change, we're selecting one point. If we only have one point, that means there's no distance, right? But of course, h cannot equal to 0, otherwise we're dividing by 0, which doesn't make any mathematical sense. So we're still going to estimate what the instantaneous rate of change is, but now we're getting much more precise answers compared to just using delta y over delta x. This this expression here is also a lot more universal and easier for us to work with, because instead of deciding concrete values, so again 3 and 5, we could create an equation for the slope, and using that slope we could always figure out either the instantaneous rate of change or the average rate of change between any two intervals. So just to recap, I would like to have an example on this so we can actually figure out how to apply this expression. So over here, I'm just going to post the video for this. So applying the equation. For example, again, as I discussed, you could find the average rate of change and the instantaneous rate of change using this expression. So of course, for the average rate of change, just substitute a and the distance between those 2 points and then solve. Sometimes you're not going to be given a or h, but you can create an equation or an expression nevertheless, because you could still evaluate what f of a plus h minus f of a all over h equals to. Again, the biggest challenge would be finding IROC in that scenario, since we can't divide by 0, but we could still combat that by using a really small value of h. For example, here I wrote 0.01 or 0.001. However, you could keep going down that path until you realize what your values are approaching. This idea of approaching something will actually be discussed in the next chapter, so I'm hoping you're on the lookout for that. So in order to understand this fully, I still would like us to do a practice question, which I am showing you here. This question is actually, I think, question 22 from your textbook. So if you want to find the written version, you can always do that. But I essentially just copy pasted it, so there's no need for that. So here is the question. As water drains out of a 2,250 liter hot tub, the amount of water remaining in the tub is represented by the following function, where V is the volume of water in liters remaining in the tub. Of course, T is time in minutes, where T is restricted to these values. We know that T can't really be negative, so of course this makes sense. Also, if T was 151, we would get less than 1 over here, which also doesn't make much sense because quite frankly, as time goes on over there, you'd be getting values that have already existed. Okay, so now we have to determine the average rate of change of the volume during the first 60 minutes and then during the last 60 minutes. Then we'll have to use two different methods to determine the instantaneous rate of change in the volume of water, and we'll also have to sketch a graph of the function and the tangent at t is equals to 75. So let's go and do that. Okay, so I wrote out the question in our notebook, and now let's proceed to solving the question. So for A, we need to figure out the average rate of change of the volume during the first 60 minutes and the last 30. So the first 60 minutes is pretty simple. Remember, our equation or expression that we're going to be using is a plus h minus f of a divided by h. So what would have to be a in this scenario? A would have to be 0 because that's our starting point, and then h would have to be 60 because over here this value should be bigger. So if a was actually 60, we would have to subtract values because this should be 0, and so that doesn't quite make sense. Either way, let's proceed with the question. So f of a plus h would be the same as substituting 60 into our equation, right? So our equation was 0.1 150 minus 60 squared. And now f of a would have to be f of 0, and so we get 0.1 150 minus 0 squared. And again, this all will be divided by h, which in our case is 60. Putting this into our calculator, you should get negative 24. So that would be the average rate of change between 0 and 60, so the first 60 minutes. Then for 2, I guess I'd call it, we have to talk about the last 30 minutes. So the last 30 minutes would be, of course, from 150 to 120. So in this case, a would be 120, and then h would have to be 30, so we could get 150. So substituting those values into our equation, we would get something like this: 0.1 150 minus 150, right? Because that would be 120 plus 30 squared minus 0.1 150 minus 120 squared. All divided by h, which in our case was again 30. And so this will get us an answer of negative 3. The question doesn't tell us what we should, if we should interpret this or whether or not, but if we wanted to interpret this, we would just say that the average rate of change for the first 60 minutes, it would be negative 24 liters per minute, because that's the units we've been using, and the average rate of change for the last 30 minutes would be negative 3 liters per minute. Again, the negatives make perfect sense here because if we're draining the tub, the volume should not be increasing. Also, as the water flows, it's pretty intuitive that the more water there is, the faster it'll go away. But if there's less water over a big surface, you'll have to like get it into the drain, so it'll flow much slowly. For B, we have to use two different methods to determine the instantaneous rate of change at 75 minutes. So let's try and do that. So the first way would be for us to try and understand this expression here, right? So what do we know? We know that the volume function, right, would be using a and h. H in our case would have to approach 0, but for now we're just gonna let it stay as h. However, we do know what a is, and a is 75. So we have our expression v of 75 plus h minus v of 75 divided by h. So if we were to expand this and actually substitute those values in, we would get 0.175 plus h. Sorry, I forgot the 150. 150 minus 75 plus h squared minus 150 minus 75 squared, all divided by h. Okay, so now let's try and solve this. Immediately what we can do is actually open up the brackets on both sides, so here and here. Our first one would be 150 minus 75 plus h, which would be 150 minus 75 minus h squared, minus 0.1 times 75 squared, all divided by h. So of course now we could evaluate this, but we can also find out what this equals to. So you have 0.1 times 75 minus h squared, minus this here should be equal to 562.5, and again all is divided by h. If we continue down this road, let's scroll down, we can evaluate what this equals to by expanding or opening up the brackets. So now we get 0.1 times 5,625 minus 150h plus h squared minus 562.5, and again we're dividing everything by h. From here we can finally expand and distribute the 0.1 to everything, and we would get 562.5 minus 15h plus 0.1h squared minus 562.5, all divided by h. As you can see, we can cancel these two out, and we can also cancel out the h's, because we have two terms with h on the top and an h at the bottom. So if we were to take out the h, we can factor it out. So as you can see, our final answer would be negative 15 plus 0.1h. So again, since our question was asking for the instantaneous rate of change, we can actually say that over here, h is equals to 0. We can finally do this because we've actually canceled out the h that was in the denominator. And so in doing that, our final answer would be negative 15 liters per minute. Another thing that we can do is use the same formula that we used last year or last class. So that would be actually substituting in values for h. So for example, if we let h be 0.2, for example, we can do something among the following. Sorry, I need to scroll down more. There you go. So if h was 0.2, we could actually find a and b, right? So if a was remember the middle has to be 75. We could make A 749, and this would have to be 75.1. We could substitute those values into our equation, or our expression, and we would get 75.1 minus V of 74.9, and divide that by the difference, which of course would be h, so 0.2. And in doing that, we would get our new values, which should come to -15. As you can see, both of these methods will give you the exact same answer, but this would require you to estimate and also choose two numbers, which of course is not something you'd want to do in mathematics, because as the equation gets more and more complex, choosing two values doesn't give you any more of an advantage in terms of being easier than actually writing out the formula. Because remember, with this, you could actually find the average rate of change for something if you found h for that. So now let's talk about C. It's asking us to sketch a graph of the function and the tangent at t is equals to 75. So now just give me a second, I'm gonna clear the screen and I'll show you how to do that. Okay, so now that I've cleared the screen, let's actually graph the function. So the function is v of t is equals to 0.150 minus t squared. You might remember that this format over here is the vertex form of a quadratic function. However, as you can see, we don't have a plus something here, which would mean we actually don't get any y shifts to our graph. Again, since we're sketching for 75, we could, for example, make the graph something like this. We also have the restraints of 0 to 150. So if t is equals to 150, we get a 0, right? So this right here is 150, and this is our origin. Now, our function would go something along the shape of a parabola. So let's try and do that. So this is something that it would represent. Again, it would go like this on both sides. We could find out our y-intercept if we wanted to by making t equals to 0. If t is equals to 0, we would have 150 times itself. So 150 times 150 times 0.1. So that would actually get us a value of 2,250. So over here, if we had a intercept, that's what that value would equal to. Again, the way you would make this properly is by having like an actual straight line. It would look something like this. Again, this would be 2,250 on the y value, and this over here would be 150 for x. Either way, when you're doing this on paper, it should look a little bit more pretty than how it looks here. But that's not the important part. The most important part, what I would say, is the tangent. How do we draw the tangent at 75? Let's actually find where 75 would be on this graph. 75 would be halfway through, so it would be somewhere here. So now this is our point. Do we know what y is? So this would be 75, then some y value. We could find that y value by substituting 75 into the equation and solving, but we'll let that be for now. So of course, the most important part of this question is actually drawing the tangent at t is equals to 75. Luckily, in question B, we actually found the slope of the tangent, which if you remember was -15 liters per minute. So this -15 is of course our m value, which is our slope. So now, using the concepts we learned actually last chapter, we know our slope should be very, very close to these points here, but not intersecting them, and also touching the graph at only this one point. And so our graph should be something like that. Again, pretend this line here is a straight line. It's very difficult to do it with only a pen, a digital pen, but if we make it very straight, we could actually adjust it. I would say it looks something like that over there. Again, changing its color would probably let us see it a bit better. Let's make it yellow. Does yellow show up? yellow doesn't show up. But either way, that line should be what we're getting. The best way I can actually illustrate this is of course by using Desmos. So if you give me a second, I will actually show you how this function in the tangent will look like when it's drawn without shaky hands. Okay, so here is the graph of the function. As you can see, we had a 0 at 150 and a y-intercept at 2250, so our graph is fine. The most important part is the fact that I put down this green dot over here, which is representing the point 75. Again, you had to find out the y value in order to place the dot, but that's not really necessary if you know the scale. So over there, as you can see, 75, we're good. So what do we do now if we want to find the tangent? Well, we found the slope of the tangent, which is -15. However, as you can see, right now our line passes through passes through the origin, which is 0, 0. So now to solve this issue, we actually need to add a b value, right? Because the slope of the line, an equation for a line, would be found by y is equals to mx plus b. To find b in this scenario, we could substitute values into the equation that we know are true. For example, this is the point that we know, right? We know that x is 75 and y is 562.5. So let's put those in. So 562.5 is equals to -15 times 75 plus b. Again, Desmos doesn't like this abbreviation, so let's just put x and find out what it got us as our value. The value that we got was 1687.5. So if we put 1687.5, what do we get as our line? Well, as you can see here, our line intersects the graph at only one point, and that is our tangent. So that is what our tangent line would look like if we wanted to perfectly graph it. Hopefully that was a good enough explanation on how we can find the rate of change using the difference quotient. In case you're still a little bit fuzzy about how to do this, I have some homework questions for you to do. They aren't too difficult, but they will surely make you better at this concept. So here is the homework that I'm assigning for today. Questions 2, 4, and 6 are really simple. Question 8 requires you to analyze question 4, which in itself is not that difficult either. The only questions I would pay close attention to is 12, 13, and 16. These questions are the ones that are really going to test your understanding of the difference quotient. So if you have trouble with that, again, just leave a comment down below and I'll publish a separate video explaining those questions. However, I hope my explanation of this unit so far has been going well. And tomorrow, I'll try to start chapter 1.3. As you can see, my uploading schedule is not the best right now because I myself am very busy with school, but I'm gonna try my hardest to finish calculus and vectors by end of January. That is my best bet because as far as I understand, the people that are having semestered schools will be beginning calculus at the end of at the start of February, and some people that have quadmesters because of the pandemic will actually be having it either in quad 3 or in quad 4. So again, I just want to make sure that everybody gets the material before they start the course. Again, I'd like to thank anyone who's got this far in the video. You guys are awesome. I hope you have a wonderful day. Thank you for listening. Bye bye.